So, last class I solved one example considering different column loads, and I have solved only taking into consideration of strip footings. Then at the end it was not satisfying the permissible settlement, hence the dimensions has to be changed, and it may be it has been recommended you can change the foundation size to a mat or raft. Now this example 4 I will keep it, this is for mat foundation. Before I go to the example 4, let me start with combined footings, detailed description of combined footings. So, combined footings are single footings supporting 2 or more columns. These are all single footings supporting 2 or more columns, particularly in a row, 2 or more columns particularly in a row. So, what check you should have? Its need you check with your pressure bulb, then space restrictions. Start one by one. First one is your rectangular footing. Rectangular footing, let us plot it. It is L by 2, here it is L by 2, then this side is your B by 2, this side is your B by 2. It can be attempted where you can go for a rectangular footing, can be attempted no space restrictions. Number 1, line of action of the column load will be closer to the column carrying of heavier load. Line of action of the resultant column load will be closer to the column carrying heavier load. Can also be attempted, can be attempted there if there is a space restriction, if there is a space restrictions. However, on the side of column carrying of the smaller load, there is a space restrictions on the side of column carrying the smaller load. What does it mean? If there is a space here, you plan in such a way that if there are two column loads coming into there, you plan in such a way that bigger column load will be here. In this side there is no restrictions. This side there is a restriction. So, for a smaller column load, means you can attempt this rectangular load. First one is no space restriction, second is higher side, third one is you consider space restriction can be considered only when the smaller column load will be placed or smaller column will be placed nearer to your space restrictions. Second one is your trapezoidal combined footing. Let me draw. This size dimension is your B1, this size dimension is your B2, and this is your column 1 and column 2, this is your resultant load, and from here to here this is your distance x and total length is L. So, where is the case you can go for trapezoidal combined footing? Number 1, restriction both the sides, both sides. Here also restriction, this side also, from this column load also there is restrictions. When both the sides there are restrictions, in that case you can go for trapezoidal footing. What are your unknown quantities? Unknowns are A, L and small x, and two thickness B1 and B2. What is A and L? A is your total area, L is your length of the trapezoidal, x is distance from one side of the column, exterior side to your CG, and two thickness B1 and B2. So, A area is B1 plus B2 by 2 into L, you can get it if you know the L, if you know the B1, if you know the B2. Then from there you can find it out this distance x, which is equal to L by 3 into 2B1 plus B2 divided by B1 plus B2. Then you can find it out B1 is equal to A by L, 3x by L minus 1, B2 is equal to A by L minus B1. So, once again I am repeating, trapezoidal column footings, it is applicable when both the sides, this side as well as this side, both the sides there is a space restrictions. That means here there is space restriction, also this side is your space restrictions. In this case, you have to go for trapezoidal combined footing, and you need to have B1, B2 and L. Once you know B1 and B2 and L, from there you can find it out your A. Once you get total area, then from there you can find it out x distance from your CG, then you can find it out other factors also, assuming other factors also you can get it B1 and B2. Now come to the next, we will solve one by one typical problems. Next is your cantilever footing. Let me draw it cantilever footing. There is a column and this is your footing. I can say this is my plan, and this will be this is your original, and it will be redistributed. Where is the conditions? Number 1, if the space restriction between the column and the boundary of property is of acute nature. Look at here, if the space restriction between the column and the boundary property, space restriction between the column and the boundary property is of acute nature, means I am not getting anything else. This is where the column has to be placed, and there is hardly any space, there is no space. That means the boundary will start from along the column side, boundary will start from along the column side, that is your case 1. What will happen from this? What will happen? Because high eccentricity, the bearing capacity of soil will be drastically reduced, and settlement increased. So, what will happen? Suppose, see, look at here, there is a cantilever footing. Why I say it cantilever footing? The space is restricted here. This is my boundary, I cannot go beyond this. And the column has been designed so that it will be placed here. So, hardly any space, number 1. Because of that, what will happen? High eccentricity will be developed. Once high eccentricity will be developed, what will happen? Your settlements will be more. Then what is the solution? The solution will be the footing of exterior column to that of an interior column by means of strap beam. Look at here. Why it is called cantilever footing? Example, because hardly there is any space in the boundary, your column load has to be applied. Because once you apply the column load, what will happen is CG has been shifted. Then because of that it will become highly eccentricity. Because of that you are supposed to get a high settlement. What is the solutions? The putting of exterior column to that of an interior column has to be joined by means of strap beam, that is called strap beam. If I write it how it looks like your strap beam, this is your exterior column, this is somewhere else, it is your interior column. From here it is coming out, how it looks your plan. This is interior column, this one is your interior column, this is your exterior column. In exterior column hardly any space, there should be strap beam has to be connected between these two columns. If I look at in other way around, how it looks, if I take it, let me put it in that way. This is my column, say A, here say this is my column, say B, So, what will happen? This column A is connected to your restriction or boundary, then this is your column B. In between these two, suppose this is my say R1, so this is say R2. So, here it has been connected by means of a strap beam. It is called, this is my strap beam. Then what will happen? Here is your coming P1, here it is coming P2, then this is your CG capital P, and this will be distance, at a distance you can say from here to here, this is my B, and this to this is your eccentricity E. So, this point is your, this is your CG, this is your CG. Now, if I plot it, so this will be coming out to be this complete length. If I take half of this L by 2, L by 2, and from here it is your L by 2, and this to this is your S minus E distance. What will happen? What is the mechanics? what will happen? As I said, there is a column here and it is at the boundary, then there is another column. Because there is a exterior column, this load is more as compared to your interior column. What will happen if I leave it in that way? There will be eccentricity. Because of that eccentricity, settlement will be more. Then once settlement will be more, it will fail, the foundation will fail. What will happen? Considering this is your footing exterior column, this is your interior column, these two column has been joined by means of a strap or by means of a beam, that is called strap. What will happen? The moment you connect, it will take care of your P1 and P2 and CG will be coming into picture. So that this strap will connect between these two columns, again it will allow load to be distributed smoothly below your ground surface. What is a strap beam? Basically a tie, this is a tie joining the two footings. Doesn't at the same time, it does not take in transmitting any load to the soil. Are you getting this? What is the role of this strap? Role of this strap basically redistribute your load. It bring back load to CG, but at the same time load of this strap is only a tie beam. It is connecting between the two columns. At the same time it does not take in transmitting any load to your soil. Actually load will be transmitted from here to here, but this is just connected, so that your CG is shifted and CG will be coming centrally, so that there should not be any eccentricity. This is a part of this what I have covered it till here. Combined footing, first one is your rectangular footing, then second is your trapezoidal footing, third one is your cantilever footing in the form of strap. And what is your requirement or proportioning? Because of certain dimensions required, you need to have your certain dimensions. If a trial length of footing A is assumed, then E is equal to L1 by 2 minus B. R1 is your moments of P1, once R1 is known, then R2 is equal to P1 plus P2 minus R1. If R1 is greater than P1 and R2 is less than P2, that means P1E by S minus E, then area A1 is equal to R1 by ASP, allowable shape bearing pressure ASP, then B1 is equal to A1 by L1, B1 by L1. So, then square footing can be provided under column B side, which is equal to R2 by ASP root over. I will stop it here. I will start. Next is your combined footings, all proportionating, and one of the design problems. I'll start it. I'll stop it here. So combined footing proportioning. First one is your rectangular footing. Proportioning means how to get your dimensions and other part. So first one is your rectangular footing. Rectangular footing is proportionate. That means it is your dead load plus reduced live load. Maximum soil pressure has to be checked. Considering your dead load plus maximum live load. Are you getting my point? In rectangular footing, the proportionating, how you are going to start for the design. For footing dimensions, footing proportionate, you have to find it out considering dead load plus your reduced live load. And for maximum soil pressure, you have to check it, what is the soil bearing pressure, considering dead load plus maximum live load. Then the resultant of dead load plus maximum live load is in any case eccentric to the CG of actual footing with rounded off dimensions. The resultant of dead load plus maximum load is in any case eccentric to the CG of actual footing, then it has to be rounded off. Now second one is your trapezoidal combined footing. Trapezoidal combined footing, that means L, projection from either side, how much projection you can get it in trapezoidal footing. If you look at here, how much projection you are getting it from either side you consider. Then x, distance to the resultant load is found by taking moment about edge B2. Distance to the resultant load is found by taking moment about edge B2. A, area known from, you can calculate, known from means you can derive or calculate from your summation of dead load plus reduced live load and corresponding allowable soil pressure. Using A, L and X, then from there you have to find it out B1 and B2, then you round off. L, projection from the either side. X is the distance to the resultant load is found by taking moment about edge B2. A, you have to calculate, A is the area you have to calculate, means you have to find it out based on your dead load plus reduced live load, and corresponding allowable soil pressure considering both these cases. Then using area L and X, find it out B1 and B2, and at the end you round it off. Also you can, as width is varying, then soil pressure P is equal to V by A plus minus My by I. I is your moment of inertia about the centroid axis, My is your moment. So, this has to be calculated, this is about your proportionating. Then all what I have discussed now, I will solve a problem, probably in the next class it will take long time. All what I have discussed, how to design for a combined footings and what are the conditions, ground reality, rectangular footing, no space restriction is not necessarily, but there is a case of pressure bulb, overlapping of pressure bulb, in that case you can go for rectangular footing. Also if there is a space restriction, in that case exterior column or column load having less, it should be close to your space restrictions. Then trapezoidal combined footing, in trapezoidal combined footings there are space restrictions both the sides. Then in cantilever footing what will happen, absolutely there is no space. If there is a boundary, in the boundary you have your footing, it has to be placed. Then you have to apply a strap beam which will connect two unequal footings, one is at the boundary, other is here, connected by a strap beam. This strap beam has a function to only connections, nothing else. Then how you are going to do your proportionating for rectangular footing? Footing has to be, footing size has to be, footing means footing size has to be calculated based on your dead load and reduced live load. Soil pressure can be calculated based on your dead load plus maximum live load. Then it has to be whatever you are going to get it has to be round off. In trapezoidal footing, projection from either side you measure and find it out L, total length. X distance you have to calculate it by taking moment about one of the edge, that is your B2. A you have to, that means area has to be calculated from your dead load plus reduced live load and corresponding allowable soil pressure. Using ALX, find it out B1 and B2, then you just round it off. Soil pressure can be calculated, P is equal to V by A plus minus My by I is your moment of inertia, V is your total vertical forces or shear forces divided by your area. Then there is one example, just I am brief description is there. So example 1, I will solve it next class, but I am just explaining. Example 1, what is the example? First one is your column load, then it is given dead load, then it is given reduced live load, then it is given maximum live load, then it is your dead load plus reduced live load, then it is dead load plus maximum live load. So column 1, A is your exterior, B is your interior. So dead load is 800, these are all you can say that kilonewton, these are all in kilonewtons. Then here it is 1000, reduced live load is your 230 kilonewton, here it is 360 kilonewton, maximum live load is your 380 kilonewton, then 760 kilonewton, then this is your 1030, then 1360, total is coming 2390 kilonewton, then here it is 1100, then here it is 1760, total is coming 2940. What is the question? Question is check proportionating combined footing of first one is your rectangular footing, second one is your trapezoidal, third one is your cantilever, then allowable soil pressure considering dead load plus reduced live load is equal to 150 kilonewton per meter square. Also considering dead load plus maximum live load 225 kilonewton per meter square. Column spacing is given, that is your 6 meter. Footing not to be extended, also it is given, footing not to be extended 0.4 meter from center to center of column A. This is what given. Example 1, column load is given. There are two columns, one is your exterior column, other is your interior column. Dead load, reduced live load, maximum live load, it is given. We have to check the proportionating, that means dimensions, we have to find it out considering rectangular, trapezoidal and cantilevers. Allowable soil pressure is given 150 kilonewton per meter square considering dead load and live load, reduced live load. Considering dead load and maximum live load, it is 225 kilonewton per meter square. Column spacing has been taken as 6 meter. Footing not to be extended 0.4 meter from center to center of column A. This is what given. This required a complete 1 hour to solve one by one. I will check for rectangular, for trapezoidal, for cantilever footings. If it is not satisfied for the combined footing, then only recommendation is for mat foundations or maybe raft foundation. If it is not satisfied, then we can go for deep foundation. I will stop it here. Maybe next class I will solve this complete example. It will take more than an hour. At the same time, you can bring your calculator, you can check the calculations. Thank you.